Hello students, welcome to the first video in the gas laws series. In this video, we're going to remind ourselves of some of the laws that you might have looked at so far in earlier grades. So these are laws that govern the behavior of gases. Ideally, we'll look at three properties of gases. So this is going to be temperature. Then we're going to also consider pressure. And last but not least, volume. Now, of course, in terms of units, you have handled these topics or these terms before. So I hope you remember their standard units. But of course, for this particular topic, what you guys have to just keep in mind is depending on the nature of the question, the units that you might have to use can be flexible, or you should be able to convert from one unit to the other. So the idea of gas laws is we want to look at the behavior of the gas in terms of its properties when one is changed or when certain conditions have been changed. So in this case, the first thing that we want to see is how do these properties relate when you're talking about a gas? And the first thing that we want to look at is an ideal gas. So an ideal gas is basically just a gas that kind of obeys the ideal gas equation. Now, what is generally, if we're going to talk about an ideal gas, we're saying this is a gas that obeys the ideal gas equation. But basically, this is just a well-behaved gas, if I can put it like that. It's a gas which kind of obeys the most basic of laws, like very simple to predict and so on. But of course, in reality, we're saying a general gas might not obey these laws, of course, unless at certain temperatures and pressure, of course. But then what is the ideal gas equation? So we're saying an ideal gas is going to obey this equation. Now, what you notice here is that P is the pressure, V is the volume, and T is the temperature. Now, how about N and R? Well, N is the number of moles present in that volume. So you might remember this term, number of moles, from your studies of chemistry. So all those concepts you learned about number of moles, how to calculate number of moles of a particular sample, you are going to need those skills to work out questions that have to do with gases. And then of course, R here is the gas constant. Now, R can take different values, of course, depending on the units that you're working with. So look out for that as well. The values can change depending on the type of units that you want to work with. So look out for that. You want to make sure you're working with the right value. Don't just get a value that you're given and start using it. Make sure it matches the other units that you're working with. Okay, now PV is equals to nRT. That is the ideal gas equation. Now, with this equation, what we're saying is, of course, these have to be to have standard units. Of course, we've already mentioned that. Now, the first thing that we want to do is, if you can remember this law, then you should be able to come up with the three special cases that can arise from the ideal gas equation. See, from the ideal gas equation, you realize that if you have a gas that is contained in a container, then the ratio that you have this side will just be equal to nR. But if the gas is contained, let's say this is your container, we have a gas in this container. What this kind of implies is the number of moles that is closed here is constant, and it's going to be constant. And apart from this, we already know to say that R is already a constant. So if these two terms are constants, then we see that PV over T is equal to a constant. Let's say K. It can be any constant really, but all I'm saying is it's equal to a constant. Now, there are three special cases that can arise from this. See, these special cases combined or put together, they give us the ideal gas equation. You can argue it from that point of view. But what I like doing is, if I can remember the ideal gas equation, then the other three cases or the other three laws can easily be derived from the ideal gas equation. Now, how do they look like? The first one, what we're going to do is, what if we have a gas in a container and then we say, okay, let's hold temperature constant. So sometimes in a laboratory, you can maintain the temperature for that particular ideal gas, for that particular gas, as one variable is changing, maybe you have pressure and volume, you allow them to change, but you just hold the temperature to be constant. See, in that case, what you end up with is PV. Now, T becomes constant as well. So if I cross multiply here, T now joins the K in being constant. So now what you notice is this term on the right-hand side is now all a constant. So you have PV is equal to a constant. Now, what we have here, this relationship that we have derived, the product of the pressure and the volume given as a constant, this is what gives rise to Bow's law. Now, properly state, it's rare that you'll be asked to state these laws at this level, but if you are asked to state what Bow's law states, all you have to do is make pressure the sum of the formula. It can be pressure, it can be volume, but then you notice that you have that constant. It can be, you can even say C is our constant now, but really up to you. You can even say the whole thing constant divided by the other side. What you have is the volume, or you can say the pressure varies inversely with the volume or to the volume. So of course, when you change the proportionality symbol to an equal sign, then you end up with that constant of proportionality there. So then you use this version of the equation to define Bow's law. So all you have to do if you're going to define it, just to say, okay, the pressure of an ideal gas is inversely proportional to the volume, provided temperature is kept constant. So that's the only thing here. Temperature must be constant. You can even say temp is constant. So mostly here, of course, remember when I started describing these special cases, we said you have a gas in a container and the container is closed. So sometimes when defining the same laws, certain key things will be mentioned as well. They will say for a fixed gas, so for a fixed mass of a dry gas, so this might be mentioned when stating these laws. So the mass of the gas has to be fixed. And apart from that, this has to be looked at in terms of a dry gas. So all we're trying to talk about is an ideal gas here. So if the mass is fixed and the temperature is maintained constant, then the pressure of that gas will vary inversely to the volume. This is basically what Bow's law is all about. Now, the next thing that we're going to look at, or the next case that we're going to look at, so again, so we're moving on to case 2. So we're starting with PV over T is equal to a constant. But for this case, in the previous case, we kept temperature to be constant, and we ended up with PV is equal to a constant, and we call that the Bow's law. Now, for case 2, what happens is, let's say now pressure is the one that we want to keep constant. We'll let temperature vary with volume now. Now, how do they relate? See, now we have volume over T. Since pressure is constant, meaning these are supposed to give us that constant. So the pressure can join the constant on the right-hand side. We only remain with volume over temperature, giving us a constant. If you're going to state it as, maybe you're asked to state what this law is, then of course you guys should be able to see that now you have V varying directly to the temperature. Now, of course, this gives rise to what we call Charles' law. Now, how do we state it? Again, the same conditions, a fixed mass of a dry gas. So we want to say for a fixed mass of a dry gas, the volume of that gas will vary directly to the absolute temperature. So I'm specifying absolute temperature because you have to use the temperature in kelvins here. Even when using the ideal gas equation itself, temperature have to be used in terms of kelvins. Sometimes to be okay to work with degrees Celsius, but for simplicity, unless the question asks you to use the degrees Celsius, but the best thing is always work with the kelvins. Okay, so of course we're saying for a fixed mass of a dry gas, the volume of that gas will vary directly to the temperature. So increase the temperature, the volume increases. Increase the volume, the temperature will increase as well. Okay. Now, what is happening here? Well, firstly, we're saying pressure is maintained to be constant. And apart from just being constant, the gas is of fixed mass, meaning the number of moles is not changing. Okay. Now, this, of course, is what gives rise to Charles' law. And the last case, case 3, this is going to give rise to what we call the Guy-Lussac's law. Guy-Lussac's law. Now, this, of course, happens at constant volume. So when V is constant. Now, what happens? As you might have already guessed, you notice that if V is the one constant, then you have P over temperature equal to a constant. And if you have to state this law, then all you have to say is change the equal sign to proportionality, then you have this. Then you can then define this law as for a fixed mass of a dry gas, the pressure varies directly to the temperature. So increase the temperature, the pressure increases. Reduce the pressure, the temperature reduces. So this is Guy-Lussac's law. That's how you state it. Now, sometimes you might have the same gas. So we're moving away from the special cases. Now I want to look at certain other scenarios that are possible in dealing with ideal gases. So sometimes you might have a gas in a container and then certain things are just changed about this gas. It might be that maybe the volume. So again, we're starting with the ideal gas equation itself, PV over T is equals to that constant and R. So in this case, we're saying if you have a gas in a container and then it's only certain cases, or let's say certain conditions that are changing for this gas. Let's say maybe it's the same container, the same volume, but then maybe just the temperature is changed. You decide to heat this container. Well, what happens is since the container is closed, meaning the number of moles will not change, R is already a constant. So what will happen is that we're just going to observe a shift. If the temperature is changed, then the pressure is going to readjust itself and the volume will also readjust itself such that if you've changed these values from their initial values, what will happen is that the value you get will be equal to the one you had at first, even though the pressure has changed, the volume has changed when you changed the temperature. So this is one equation that might come handy when you're working some of the problems. So mostly you want to use this equation, but look at the question itself. Try to pay attention really. If they're saying it's at constant temperature, at constant volume, and so on, then you not say, okay, you're in the territory of the special cases. Okay, but otherwise, if it's just all the three things are changing, the three properties are changing, then you're going to use the original ideal gas equation, which is going to look like this. Where necessary, of course, from a chemistry point of view, the number of moles, we're going to calculate it by, of course, dividing the mass by the molar mass of the sample. I hope you guys know how to use this formula. I hope you know how to calculate the molar mass of a given compound. So this is something that you guys are going to be using a lot. The special cases can also be written in this form. Now, how will they look like? If we start with Charles' law, where V over T will always be equal to a constant, now we're saying V1 over T1 will be equal to V2 over T2. And then, of course, in the same manner, we have P1 over T1 is equal to P2 over T2. And lastly, that's Bow's law now. We have P1 V1 equal to P2 V2. Okay, now this was just a quick run through the gas laws. Now let's quickly go and look at some of the questions we can work out. Okay, so you guys can pause the video and try to go through the question. It kind of has a hint on the approach you're supposed to take. So you can pause the video and try to see if you can work out this question. Read through, try to understand it. I'll give you a few seconds And after that, we can start with the solution. Okay, so I hope you had time to try out the question. I hope you went through and read through everything. So what the question is kind of describing here is a situation where you have a gas in a container. Now, this gas, of course, we're saying we have two parts, two sections. So it's like on one side, we have a smaller volume. This volume is said to be 5 liters. And then the other side, we have a larger container. And then this larger container is said to have a volume 20 liters. So the other side, we have volume V1 equal to 5 liters. Okay, now the next thing they're saying we have the same gas. Somewhere here we have a stopper. So the same gas is here. We're told everything about it. So we have the volume of this gas this side. We have the pressure of the gas this side. This is given to us as that's 2.5 by 10 to the power 5 pascals. Then apart from that, we also have the temperature of this gas this side. It is initially at 20 degrees Celsius. So remember, you always want to work with kelvins unless otherwise. So we can write this 20 degrees Celsius, you can convert it to kelvins. This becomes 293 kelvins. And then on the other hand, the other side, we have a similar gas. Okay, so yeah, don't think this is water. Sorry for using those lines. So this is a gas this side as well. So let's see what we're given. We're given the volume of the gas. We're given the temperature of the gas as well. And then this is 25 degrees Celsius. So of course, in kelvins, this will be 298 kelvins. And then next up, basically this is all that we're given. And then the question is asking us to find the pressure this side, P2. Now, what is happening is initially this stopper is closed. We're told we can neglect the volume of the connecting tube here. So we're only dealing with the volume this side and the volume this side. Now, what is happening is initially this part is closed, meaning these are the conditions. These are the conditions this side, and these are the conditions this side. But after opening the stopper, these gases start to interact. Now, when they interact, what happens? Well, the volume changes. See, the question doesn't say how the volume changes, the volume of our system here. The question doesn't mention anything about it. They're just saying after the stop has been removed from the connecting pipe, the new equilibrium is found to have the temperature of 23 degrees Celsius. So they're saying after we now have temperature, you can even call this to be T3. This is now 23 degrees Celsius. So of course, in kelvins, this is going to be 296 kelvins. And then if we go back to the question, they're saying in the pressure of 1.5 by 10 to the power 5 pascals. So the pressure P3, they're saying this is 1.5 by 10 to the power 5 pascals. Anything else? That's all. The next part, they're saying find the pressure P2. Now look at our hint. Calculate the number of moles. Now, how does that help us? See, when it was closed here, we had a specific number of moles each side. Let's say here you had N1, and then the other side you had N2. These are the number of moles. See, since this is a closed system, it means that the number of moles you have here, it's going to be fixed. It's going to be constant. And the number of moles you have on the right-hand side, it's also going to be constant. When you open this stopper, what will happen is that the number of moles are now going to be interacting. The new system that we now have, the one where the two are now intertwined, or we can say they're acting as one now. The total number of moles in the system now is going to be N1 plus N2. So since we want to find what P2 is, they're saying we take the number of moles root. How does that work? Well, on the left-hand side, if we use the ideal gas equation where we have PV is equal to nRT, we notice that we can easily say N is equals to PV divided by RT. So from here, if we start with the left-hand side, before we open up the system, the left-hand side, the number of moles N1 will be equal to the pressure P1, the volume V1 over R is a constant, but now divided by the temperature T1. Now, the pressure, what is the pressure P1? Well, it is given already, so no struggle there. That's 2.5 by 10 to the power 5. The volume is given to us in liters. We can work with it like that, but I'd rather work with standards, of course. So we're going to convert it to meter cubic. If we do that, if we did that, then the volume that we're going to use here is going to be 0.005 meter cubic. So this is divided by the Raybecks constant, the gas constant, sorry. The gas constant we're going to use 8.314. And then lastly, the temperature in kelvins, this is 293 kelvins. So of course, when you simplify this, you get N1 is equal to 0.5131. I like writing the whole thing and then just rounding off my final answer. Sometimes, of course, it gets tedious having to write all these values. It's easy to make a mistake. So sometimes you might want to start rounding off early, but I prefer rounding off at the very, very end. Now, what this gives me is at the beginning, before the stop was opened, the value I found N1 is the number of moles on the left-hand side. Now, what else? See, what I want to do is after the tap was opened, after the stop was opened, this side, well, I kind of know the volume. It's not mentioned in the question, but I do know the final volume. Since the two sections became one, it means that the volume is supposed to be V1 plus V2. So the volume here after the stop was opened, it has to be 25 liters. And 25 liters, if I converted that, I get 0.025 meter cubic. So now working with this again, I want to find the number of moles here, N3. So this is V3. So I want to find the number of moles N3. Why do I want to find this number of moles? So that they can help me determine the number of moles N2. I know when I add N2 and N1, I get N3, meaning that to get N2, I can easily say N3 minus N1. This is going to give me what N2 is. And once I know what N2 is, I can easily use the ideal gas equation again now for the right-hand side to get what P2 is. I hope with that, if you struggled to work it out the first time, you have an idea of exactly what you need to do. You can pause the video and try to finish working out this problem. Okay, now let's quickly go to what happens after the tap has been opened. So we want to find the number of moles N3 after the tap has been opened, after the stop has been opened. So what we have, the equation we're using, it is, so it's PV, so it's pressure 3, the volume 3 divided by RT3, where T3 is the temperature after the two gases combined. Okay, so P3, the pressure after it's given to us, that's 1.5 by 10 to the power 5. And then the volume V3, it is also given to us. We calculated that, that was 0.025. And then this is divided by the constant, that is 8.314. And then this multiplies the temperature in kelvins. So that is 296. And then if you perform the calculation, we get N3 as 1.5 805,499 ohms. Okay, now having obtained what N2 and N3, what N1 and N3, what they are, we can easily calculate what N2 is. So N2, as we saw earlier on, so we did mention to say, to get N3, all we had to do was to add N1 plus N2. So meaning to get N2, we just have to subtract from N3, subtract N1, meaning that we get those two values for N1 and for N2. So I just write them to 4 significant figures. For now, you guys can type the whole thing on a calculator and then see what you get there. I'll always be using the full one. I won't round off just now, but just for writing, I'll write the short one. Okay, so N3, if we get N3, that's 1.523. And then from this one, we subtract N1. So we found N1 earlier on, that's 0.5131. So when you subtract these, you get N2 as, so this is not 0 point. This comes out as 1.01. Again, I'm using the values I get when I subtract the full one. So again, I'll write it just short, 0.6. But you guys can keep writing the whole thing. That's what I'm using for my calculations. So of course, after getting this value, now we can go back to the ideal gas equation. Now this is on the right-hand side before the tap was open. Because from here, this is the number of moles that was present on the right-hand side. These are the number of moles which are present, meaning I can use those number of moles to find the pressure that was there on the right-hand side before the tap was opened. Why am I saying so? Because the pressure 2 is equal to the number of moles on the right-hand side before the tap was opened, multiplying the constant, the temperature, divided by the volume on the right-hand side before the tap was opened. So N2, we've just seen what it is. Again, I'm using the full one when calculating here. The constant, that is 8.314, multiplying T2, that's the temperature on the right-hand side. In kelvins, that's 298. And then this has to be divided by V2. V2 is 20 liters, convert that, and you have 0.02. So if you work out this, you get P2 as 125,200. This is a long value. I'll just end it up there. Write it in scientific notation to 3 significant figures, and this becomes 1.25 by 10 to the power 5 pascals. Okay, so this is how you get the pressure on one side of the system, which is on the right-hand side before the stop was opened. So I hope you guys were able to follow. Let me know your reactions in the comment section. So were you able to work it out? Was that brief reminder of the things that you learned earlier on, was it helpful? Okay, otherwise for the next video, you can try out another question that you might find interesting. It is not very complicated, really. You can just try to think about it. So it uses similar ideas. So you guys can just try it out. Let's see what you find. I hope you will be able to find it. Okay. All right. Otherwise, this was your tutor. We'll see you in the next tutorial.